Have you had a look at it? Good. Can be found in the big handout if you don't have a small one. Oh no, I would almost forget. So Karen and George won in the homework competition, but George is not here. Good luck. And okay. Now, question. Congratulations to the winners. Question 9. Aha. How does one solve a question like this? First term stuff. Any idea? Okay, so in this question we have an LP. We have the final tableau. There's not much to do about that. But the question says the right-hand side, so this 3 here is going to change. And it asks us, how much can it change up and down so that we don't have to pivot, okay? Because we might have to pivot. So similarly to what we had in the question in the previous lecture, so at 10 o'clock, when you're changing the right-hand sides, what's the only thing that's going to change in the tableau? I think Dante said it in the previous one, and it's only this bit, okay? So the only thing that is going to change in the tableau is that. Now, what is it going to change to? So the val column so okay, let's do it properly. The val column again. The val column currently is 37734, which, as we know, we can get by looking at these columns here, the S1, S2, S3 columns, and taking 15 times S1 plus 3 times S2 plus 4 times S3. So it will be 15 times 1012 plus 3 times 0100 plus 4 times minus 3, 1, minus 2, 1. Okay, that's the kind of MB inverse times B computation. So when you're multiplying a matrix, as I'm sure you know, you multiply a matrix by a vector, so the vector comes right. That gives you a combination of the columns of that matrix. Okay, so every entry in that vector is going to multiply one of the columns of the matrix, and then you add them all together. Now, that's what you get. So that's how matrix multiplication works. So the val column is going to change. Well, the 15 stays 15. Okay. 1, 0, 1, 2. Now the 3 is going to change, and we don't know what it's going to change, so I'm just going to call it B2. So that's the new B2. 0, 1, 0, 0. Plus 4. The 4 is not going to change, so we've got 4 minus 3 minus 2. Sorry, minus 3, 1, minus 2, 1. So we get 3. That's still there. Now here we get 4 plus B2.
Yeah, slide it.
Oh, I'll try. Oh, yeah, sorry. It's completely in the wrong place. Four plus B2, what am I doing? I forget what I'm doing. 15 minus 8 is 7, and 34. Is it making sense? No? Yeah. So in general, if you've got that bit, okay, in a tableau, and you want the val, what you do is you look at the right-hand side in the constraints. First right-hand side times the S1 column, second right-hand side times the S2 column, third right-hand side times the S3 column, and so on. And you add them all together, that's what you're getting. So this is what we were getting. The original right-hand side, we change one of them, and we're getting something else, depending on what the new right-hand side is going to be. Okay, so this is what is going to sit in the val. So how could this new tableau not be optimal? What could happen when you would have to pivot? There's only one thing that could go wrong. What is it? What could go wrong? Anybody? How would you know that this is the optimal final tableau?
That's it at the top.
Sorry, no negative. Someone said no negative. Yeah. You said optimal at the top.
Yeah, I said it says it at the top.
Does, yeah. How would you know now?
Just get it down a little bit.
No negative, I take that as a better answer. No negative where?
No.
Two places, like two places. No negative here. Zero. Okay. No negative here. If you have a negative there, you need to final pivot. If you have a negative there, you need to dual pivot. So the only thing that could go wrong is if you get a negative number there. So feasibility is maintained if that is not negative. If the right hand side is -4 or more, we don't have to do anything. It also wants us to say what the allowable range is. Okay. And that's all the values for which the tableau remains feasible and optimal. So anything from -4 to infinity. So that solves part 1. How about part 2? What is part 2 last? Don't worry. Okay, C2 changes. I'll do the delta approach. So C2 will now be, it used to be -5. So I'll say it's -5 plus delta. Okay, so it changes by an amount delta. What's going to change now? Does this part depend on the objective function? Does this part depend on the objective function? No. Does this part depend on the objective function? Does this part depend on the objective function? Does this part depend on the objective function? And this? Of course it does. Okay, so what's going to be new is the obj row. Okay, well, for the basic variables, it has to be 0. Not enough space there. What can I do? So you get 34 plus 3 delta because it changes by a delta multiple of the x2 row. We're talking about the coefficient of x2, so I'm looking at the x2 row. I'm changing x2 by, sorry, c2 by delta, so I'm taking a delta multiple of the first row and I'm adding it. So this is going to be 4 minus delta, and this is going to be 2 plus delta. And this is going to be 1 minus 3 delta. So what are the conditions for this to be optimal? Then again, something is greater than or equal to 0, that I take as a good thing. The val actually can be anything. We don't care. There's no requirement usually that the objective should be non-negative. So that one, no, but the other ones have to be non-negative. Otherwise, we'd have a negative thing and we'd have to pivot. So yeah, the val is special because usually we don't say that the objective has to be non-negative. Very often it is because of the problem, but when you've got negative coefficients in the objective function, it might happen that the optimal objective is negative. That's not a problem. Okay, but the other numbers have to be non-negative. So 4 minus delta has to be non-negative, and 2 plus delta has to be non-negative, and 1 minus 3 delta has to be non-negative. Okay, so what does that mean for the delta? You should, yeah. So this is delta is minus delta is greater than or equal to minus 4. Delta is less than or equal to 4. Okay. How about this one? Delta is greater than or equal to minus 2. And minus 3 delta is greater than or equal to minus 1. So delta is less than or equal to 1/3. One of them we don't need. This one. Because if delta is no more than 1/3, and certainly is no more than 4. So we're looking for any delta between minus 2 and 1/3. And it can stay minus 2, and it can be 1/3. So that's the interval for delta. And therefore, the allowable Remember, we started with a -5, and we can decrease it by 2, so it could go down to -7, or it could go up to -14 thirds. So as long as you keep C2 in this interval between -7 and -14 thirds, then that tableau, well, not the tableau, but the base is going to stay optimal. The tableau is going to change, but we won't have to do it. That's also part 2. Any questions? Because if delta is no more than 1/3, and it says to me it's no more than 4. So it doesn't put any extra constraint in delta. It's called redundant. Yeah, so when you get inequalities like that, and they all have to be satisfied, and you're always looking for like the smallest upper bound and the largest lower bound, and that's the two numbers that define the interval. Okay, and then that already gives you half the marks. It's not too bad. 20 minutes. Yeah. You know what you're doing. Part B. Quite similar to the homework problem we had. So we want to find the shortest path from here to there. Using integer programming. Yeah, if you don't know how to do that, then you're probably doomed and won't be able to do it. But if you did the homework question, or at least went through the solution here, then you know how to do it, and so it's not very hard to do, because you know that for every edge, you need a 0, 1 decision variable, which says whether you're going along that edge where you actually need 2, because you need 1 for each direction. So the decision variables if I really want them all, then it's x1, 2, and x2, 1. And then for this edge, okay, then I have x1, 3, and x3, 1. For this edge, and I have x2, 4, and x4, 2. For this edge, and I have x3, 4, and x4, 3. For this one, and x3, 5, x5, 3, and x4, 5, and x5, 4. And they're all binary decision variables. And XUV is 1 means that shortest path uses B, no, V1V is not a good term. Xij is 1, uses Vi, Vj, that edge, we've got him from Vi to Vj, and 0 otherwise. I want to use the shortest possible thing, so, wow, it's a bit, and so let Dij be the length. Of the edge that goes from Vi to Vj, so that's these numbers on the edges. And what I want to do is minimize the distances of the edges that we're using over all I and j. I'm just going to pick all I and j. Good enough. Okay, so what's going on? Okay, so I could have a path, like a green, that goes from here to there, from here to there, and from here to there, and from here to there. Now, I'm not sure whether that's the shortest path, but that's just an example that goes from 1 to 5. Okay, and then I would put, because I'm using 1 to 2, I would put x12 is 1, and because I'm going from 2 to 4, x24 is 1, and because I'm going from 4 to 3, x43 is 1, and because I'm going from 3 to 5, x35 is 1. Okay. And all the other decision variables would be 0 for this specific part. Okay, does that make any sense? What I'm trying to do is, for the ones that I am using, so that's the ones that are ones in the decision variables, when I look at their lengths and add them together, I'm trying to get the least possible number among all paths from 1 to 5, V1 to V5. Okay, that's what this does. And then the constraint I need to make sure that I actually leave V1. And I can leave V1 either going to 2 or going to 3. When you look at the picture. Yeah. So from 1 to 3 or from 1 to 2, I want to use one of them. Could put greater than or equal to 1, so that will give me the same optimal solution. I'm not going to come back. That wouldn't be the shortest. If I came back and then went again, I could just avoid doing that loop and start right away and make it shorter. So in the shortest path, I'm only going to turn up every vertex, either not at all or once. Okay. And then I have to make sure that I arrive at the vertex V5, and I can either arrive from 3 or from 4. So I want x35 plus x45 to be 1 because I want to arrive. I have to use one of these two edges to come there. And then in the remaining vertices, which is 2, 3, and 4, I have to make sure that if I do arrive, I also leave. Okay, so in vertex 2, if I do arrive, that's x12, then I will have to use x24 as well. And if I arrive from 4, then I will have to leave as well. Or something like that. And some sort of rubbish. Now in vertex 2, why did I do it this way? Thing I want, if I arrive no matter where from, then I need to leave no matter where to. So that's a better one. Sorry. So I need one like that for vertex 3 as well. So if I arrive at vertex 3, which I can do from either 1 or from 4 or from 5, and I want to leave 3 so that I can go either to 1 or to 4 or to 5. And finally for 4, and I want all these decision values to be binary. Yeah. Okay, do you need to know anything else? No? Well then, enjoy